I return to this slide just briefly, just to point out something that maybe wasn't completely noticed before. When we have a typical fragmentation pattern in alkanes, the radical that is lost will always have an odd nominal mass. So notice it's m minus 15, 29, 43, 57. All of those are odd numbers. So in part, recognizing the 15, 29, 43, and 57 is helpful, but also recognizing that those are odd numbers. Now looking at this situation, and this is the situation of fragmentation in alcohols. And by the way, we're only looking at a couple of possible fragmentation patterns. There are whole books on the kinds of fragmentations that can happen with various functional groups. So one possibility with an alcohol is starting with the molecular ion. What can happen is an OH and an H can combine ultimately and be lost as water. Notice that the resulting cationic fragment is actually a radical cation. So the water is lost as a proper water molecule. It's not a radical, and we're left with a radical cation. So we start with a radical cation, and we end up with a radical cation. And note, if you were to calculate the difference between the original molecular ion and the new peak, you'd see that what gets lost is a mass of 18. So in part that should alert you, oh, maybe this is water that gets lost. But also notice that this is an even number. So this is not the typical kind of fragmentation pattern that we normally see in fragmentations of alkanes. So be aware of that. And I'm going to look at one last example. This is called the Mclafferty Rearrangement, and it's associated with fragmentations that involve ketones and aldehydes, but for that matter, it's fragmentations where you have this carbonyl group. So other groups or other functional groups that have this carbonyl group, of course, include things like esters, carboxylic acids, and even amides. So all of these can undergo a Mclafferty rearrangement, but there's another criteria that's required beyond having a carbonyl. And that other criteria has to do with this idea of the gamma position. So let's take a look at the representative ketone that we have here. So this is a 1, 2, 3, 4, 5, 6, 7. So this is heptane 2-one, 7-carbon ketone. Now, the idea of gamma position has to do with this sort of labeling. So I'm just going to change my pen color. This is considered to be the alpha carbon, beta carbon, and then now this is the gamma carbon. And in order to have a Mclafferty rearrangement, we need to have a hydrogen on the gamma carbon. So that's obviously therefore the gamma hydrogen, and that's on the gamma carbon. I'm going to show you some curved arrows to represent the Mclafferty rearrangement. I think it's a good idea, and I will be expecting to see this, to learn about the curved arrows because it helps you predict what the products are going to be. I realize that in the course we haven't yet actually formally introduced the use of curved arrows, but that's coming shortly. What might be helpful is to erase this circle so that I can more easily show you the curved arrows. Now, effectively what's going to happen is we're going to end up with having a situation of no longer having the carbonyl group. And so if you can kind of think, and maybe always start in the same way, that this pi bond is going to get broken, and it's going to get broken in a sense by picking up that hydrogen. So that, in a sense, is the first step. The next step is that we're going to be forming an alkene between the gamma and the beta carbons. So this pair of electrons is going to come down here. Then next, we're actually going to break the bond between the alpha and the beta. And the electrons involved in that bond are now going to form a new pi bond here. If I label the final products on the right-hand side, it might be helpful to remember that this is the alpha carbon, and over here we have the gamma and the beta carbons. And so the curved arrows guide us in anticipating those products. You'll notice that the fragment that is lost, which is this guy right here, would have a mass of 56. And also notice that that's an even number. So once again, if you see the loss of a fragment with an even number, you know that this is not a typical alkane or alkyl fragmentation. Notice that what's left behind, the cation, is also a radical cation. And of course what gets lost is therefore not a radical. Just to verify the mass, so when we go to predict the formula, because this is an alkene and not an alkane, this would be C4H8. So 4 times 12 is 48, plus the 8, well, of course, that's 56. And therefore, of course, this mass corresponds to the mass that was lost. It's important that you practice this sort of rearrangement so that you can reproduce this in a test situation. And I have a number of examples in assignments. I think this paragraph right here is important, so let's read it together. This fragmentation is unusual in that most fragmentation events result in radical fragments, as we've seen, with an odd number of electrons that have an odd mass. And as I've mentioned, minus 15, minus 29, minus 43. To highlight this, let's look at the example on the next slide here. These are the common kinds of fragmentations that we would expect. Once again, you see those numbers for the typical kinds of fragments that get lost, minus 15, minus 29, minus 43, minus 57. All of those are odd numbers. And then there are 2 examples of even numbers, and they alert us to the idea that perhaps water is lost from an alcohol, or we have this Mclafferty rearrangement.